same as this. U, sorry. So that's the relation by this relation. And then we'll take sections.
No, I mean, okay, I'm exaggerating.
It's a little,
Okay. I'm going to start off without the projector since I don't have it. So I want to talk.
So where is the projector?
It's coming. It's coming. But I don't need it. The part of my talk is not. Part of my talk is not projectable, so to speak. So I want to remind you of what the gamma function is because we're going to need a calculation which involves the gamma function. I'm not sure I'll get to it today, but I'll get to it either today or next time. Wonder, Dragan, can you set this up while I'm talking?
I can try.
You can try, yeah, that's right. What is the gamma function? Mr. Adrian. Is that your name, Adrian?
yes,
What is the gamma function?
I have no idea.
Okay, the correct answer is it's the most important function in all of mathematics next to the zeta function. Okay, I'll ask you again. What's the gamma function?
The most important function next to it.
You're learning quickly.
Nah, he's only half learning quickly. Not too slow, not too fast, just. Okay, so let's see. What is the gamma function? Mr. I'm sorry, I don't know your name. What is your name, first of all?
First of all, my name is Toshi.
Toshi. Oh, you're Toshi, right. I should know you who you are. And what is the gamma function? Muskashi desu ne. Hello, yes, sir.
It's a generalization extrusion.
Okay, that's a good. That's at least something intelligent has been said. Not 100% intelligent, but good. That's good. So this is why. Let me say again, just so you understand, the gamma function is the second most important function in all of mathematics. It's just so we know what level of math we're talking about here. It generalizes the factorial function. That's not why it's the most important function in mathematics, but it's part of the game.
Yeah, that's the exponential function, rank.
Hello?
Where's the exponential function? Is it on rank 3?
Oh, yeah. I just
Wait.
realized it. Okay.
I'm sorry,
I
this-
need
Lots of interference here, yes. What is your
The exponential function, is it on rank 3?
rank 3?
level of importance.
Oh, level of importance. Oh, no, but it's much more interesting than the exponential function. No, I mean, the exponential function is important, but it's not so exciting, right? I mean, you've seen one exponential function, you've seen them all. It's not so good. The gamma function is really a very, first of all, it's extremely mysterious. After 300 years of looking at the gamma function, it's still an extremely mysterious function. Did anybody actually know the definition of the bugger? Mr. Rosenfield, yes.
It's an integral.
Yes, what integral?
From in t from 0 to infinity. Well, it's a function of an integral, but it's integral from 0 to infinity. T to the s. E to the minus t. Okay, is it minus t squared? It's minus
This is correct.
over t. And you need to divide by t.
Yes.
Yeah. Because it's multiplicative parametric.
There we go. This is good, very good. Okay, so he's exactly right. So there's a huge controversy out there in the real world as to whether, so if you put this t over there, then this becomes an s minus 1, and half the world, mostly applied mathematicians, just write s without this, and the other half writes this. But the reason this should be here is because this is a multiplicative Haar measure, and what this really is, it's some kind of Fourier transform of an exponential function. So somehow the dt over t really does belong there. Okay, that's the definition. What's the relation?
Is it worth explaining what the words multiplicative Haar measure mean?
Not yet, no. not yet. So when I need it, I'll do it. I haven't. That's a good point. I mean, nobody else, we haven't mentioned that, huh?
I thought this may be a natural place to mention.
I'll keep it in mind. I'm not going to do it yet because okay, but it's true. We should at some point, when I calculate some integrals later on, we'll actually need to know that. Okay, what's the relation between the gamma function and the factorial function? Mr. Red Hair Krukat there.
I think gamma of s plus 1 is s factorial or something. When s is an integer.
Okay, we'll put that like that. Okay, so it's a useful function. So it kind of interpolates the gamma function. It, for which values of s is this integral defined? No, that's not quite right.
Real part greater than -1, or is it greater than 0?
That's what you tell me. Who's answering? Mr. Rosenfield again? Yes?
Greater than 0. Real part
Yes, that's right. So this function is not quite integrable, but it's very, very close. And as soon as I add a little bit of a thing there, and this is exponentially decreasing, which where so this is real part of s greater than 0. That's cool. Now, that's not everything that can be said about the meaning of the gamma function. What's the next thing about the gamma function?
Holomorphic in S?
It's, no,
All right.
meromorphic in S, yes. Can be,
I guess right, right half plane.
huh?
Holomorphic in the right half plane.
Yeah,
Where
but
the thing converges.
yes, of course. No, but that's obvious. You don't get any points for that. Do it.
You don't want to give him any points?
Oh, I see. Yeah, I should. It's true. It's true. If we're giving part marks here, then yeah, we'll give them part marks for saying it's holomorphic. Where the heck are the erasers? There's one. Okay. So it's holomorphic in S. But it's meromorphic everywhere. Okay, how do we show that? Let's try, let's see, somebody. Why is it meromorphic in S everywhere? The gamma function.
Asking the wrong person.
Using the functional equation.
Yeah, what?
S plus 1 is S times gamma S.
Yeah, how do you get that? Yeah, that's right. So I won't write down the integral, but integration by parts gives gamma of S plus 1 is equal to S times gamma of S. Of course, that matches what happens for the factorial. But the better half is that then gamma of S is equal to gamma of S plus 1 over S. And so since this is defined for real part of S bigger than 0, this is defined for real part of S bigger than -1, except at S equals 0. And so you continue on. And so we have gamma of S. Okay. And so okay, except at -1, well, 0, -1, and so on. Okay, so that's pretty much the basics of the fact. The Stirling's formula, which is nice to know. What's Stirling's formula? I'm not going to prove any of this. But I didn't have time to do this on the slide. What's Stirling's formula? You with the, yeah, you. No, you. Yeah.
I don't know the formula here, but it's the formula is the asymptotic behavior.
Yeah, what's asymptotic behavior? What is the formula, though? You don't know.
I don't know that often.
So, actually, I have to confess, I'm not quite sure what it is myself. It's something like this. What do I have here? I have actually, I can cheat, of course. That's my prerogative. Somewhere. God, it's buried in here. It's really buried. Oh, here we go. Yeah, it's S times S minus 1/2. The trouble is, it's Stirling's formula for this versus Stirling's formula for the factorial. It gets kind of confusing. Okay, I think that's right. If it's not, it's basically right. And it turns out that this is good for all S in a region that looks like this. So as long as this angle is positive, then this works as S goes to infinity. Okay. That's not actually quite so trivial. It's much easier to show that for real values of S it works out all right, and pretty much that's all we'll need. That's not, and sooner or later we'll have to worry about complex values as well, but basically we'll be real values, and that's much easier to show by some elementary calculus argument. The hardest part is to get the square root of 2 pi, but I won't say anything about that. Okay, now there's one more thing we have to know about the gamma function. These notes are online, but I'm not sure that's a virtue because there's so much more, there's tons of stuff in here, much more than you need to know. And that's the following formula. So this is what we need to know. So I'll say something about why the gamma function is important, but one reason it's important is because it's constantly occurring in volume calculations. Actually, I have it like this, but in fact, I'm going to rewrite this. Let's put a beta over 2 on the bottom, and then it becomes beta over 2, and this becomes a beta over 2. Okay. So that's an important formula. You should write that down. You shouldn't have to memorize this, but when doing calculations with real groups, you should always have this formula at hand because this integral pops up all over the place. In a sense, the only case, I think we'll get to it today, one of the interesting cases is this one. This goes from 0 to infinity, but I can multiply by 2 under some circumstances and take the whole integral. And in particular, if I do this, what's this integral? Nilofer.
Sorry, I was looking at the.
Sure, that's fine. You can look again. What's that integral?
I guess it's
6, 7, 8, 9, 10, 11, 12. No idea.
pi or something.
It's yeah, so the indefinite integral is arctan, and arctan of infinity is pi over 2, and so it's pi. Okay. Okay. I can't resist just pulling a rabbit out of a hat. The reason that's true is because if I draw a circle, I'll just simply draw the picture and I'll let you contemplate it because of this picture. So. That's the reason it works out. Okay. Okay, so that's pretty much all we need to know. Now let me get this set up. Oh, great. Hello? This? Oh, T, yeah, sorry. I don't know. I just couldn't read. Actually, I have no idea why I wrote that. Okay. 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 Well, very nice. The Mac has memorized my place. That's really great. No. No. Yes. Excuse me for a minute. Something. Oh. And this. No. The screen is very dark. That's why I'm having trouble. I don't know why it's not. Is it plugged in? Yes? Does anybody know what to do to make a Mac screen less dark?
Let's see. Maybe. Let's.
Something.
Oh, let's see. Build this.
Why? Oh,
Yeah.
okay, there we go. Okay, great. Okay. What? I don't know. See? Okay. Oh, I know what's wrong. I know what's wrong. I'm not thinking. I'm not thinking at all. Okay. PSA type. There we go. There we go. Stupid. Oops. Stupid me. Sorry about all this. No. No. I just want to. I won't. I'll try not to swear, so I'm going to try to do. I'm very close to very, very nasty words here.
You need some mouse practice.
Let me. I know. No, I was told yesterday I'd drag it into the Adobe Reader, right?
Wait until it highlights.
What the heck is going? I'm dragging it in. I drag it over.
There.
There we go. Okay. Yay. Yeah, right. I don't know. If you clap, you're clapping for Steve Jobs, not for me. Okay. 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 No? How do I turn off lights? The other side? Oh, okay. Okay. So let's see where we are. Now here's today's talk. There we go. Okay, now, we have this notion left over from this morning, which you don't have to know anything, just sort of the words, really, just to place it in context. I like to remind people constantly that even the representation theory of real groups is really part of mathematics at whole. So the idea of a homogeneous vector bundle is something that people use all the time, and the principal series is just a special case of that. But you don't have to know what a homogeneous vector bundle is. What the principal series, however, is pretty simple. First of all, what I do is I take a character of the group capital P, the upper triangular matrices. Now, it's a character, and this group has a funny structure, so a character is a character of A. The n part just gets killed, and so we're looking at the quotient, basically, to get a character of P. So we look at a character of A, and the characters of A are all of a very simple form. They're just the absolute value of x to the s. The character, I mean, just a continuous homomorphism of C star. There's no other requirement. And you get to choose the sign, so you get plus or minus the absolute value of x to the s for an arbitrary complex number. And this is a unitary character. By definition, what unitary means is it preserves a Hermitian inner product, and it's a unitary character if and only if s is actually imaginary. Then the absolute value of this is 1 for all x. And, well, a character of A determines a character of P, and a continuous any continuous irreducible representation of P is of this form. In fact, yeah. And in fact, well, there's a typo here. This should be, oh no, that's exactly right. So at some point, maybe, I'm not sure, we might want the option of taking other finite dimensional representations of P. If we do that, then it's useful to know that in any continuous finite dimensional representation of P, n is taken to unipotent matrices. Here the unipotent matrix is just the identity. And the principal series representations of G are those induced from those of P, and the characters of P, and what that means is that I have a space which I call the induced. My notation is eccentric. I love my notation. I'm not going to change it before I die, but nobody else likes it at all. Other people write the P and the G here, but then you don't get room for the infinity, which I'm in love with. So anyway, this is my definition of the induced, the smooth induced representation. It's all C infinity functions. So these are C infinity functions of this homogeneous bundle, C infinity functions from G with values in C, such that this is satisfied. And this looks very much like the formula this morning for the homogeneous bundle, except that I've thrown in, so here's my character chi, that's the character I'm starting with, but I've thrown in this delta 1/2 factor. And that's what the whole talk this morning was really to motivate that delta 1/2 factor. It's designed to motivate things because if I take chi to be minus delta to the minus 1/2, then of course there's no thing. These are just functions on the projective line, and then I get C infinity of the quotient. But if I throw in plus 1/2, I get the thing I had this morning. Then I have delta to the 1, and that's my measures on G quotient P. And I'll denote that by this. So those are the smooth measures on G quotient P. So you have a duality between -1/2 and +1/2. And in fact, that duality continues because if I take a function, I did this rather quickly too. If I take a function in n chi and I take another function in n chi -1, then I multiply them together. The chi and the chi -1 cancel. The delta to the 1/2 here add to a delta. And so the product of these two functions is in this space, and then I can integrate it. And I write my integral like that. So there's a duality, a definite and non-degenerate duality between n chi and n chi -1 in this sense. And the whole reason for this morning's talk was just to get this duality between chi -1 and chi. If I didn't have the delta 1/2 factor, the notation would get rather confusing. And in particular, if I take my chi, if chi is unitary, then its conjugate is its dual, and that's the same thing itself. And so the representation has, in other words, there's a G-invariant Hermitian inner product, which is positive definite if chi is itself a unitary character. So that's it. That's, in a sense, that's all you have to know about the principal series. Not.
I have a good question, sir. If I want to get the sections of n forms, top dimensional differential forms,
Yeah.
what character should I choose?
Delta 1/2 here. Because in this case, notice that delta 1/2 is, remember there's this a squared, doesn't change size, so delta is the same, the twisted n forms are the same as the n forms. N is 1 in this case, right? And so the twisted n forms are the same as 1 forms, and I choose delta 1/2, that gives me this. Okay, okay? Okay. Yeah?
What do you mean by smooth measures omega infinity?
Smooth meaning they're C infinity functions.
But measures are not. Okay. Take the. I mean, a smooth function times the big measure, or something like that.
It's smooth. What is?
No, I'm talking about omega infinity.
Yeah.
What is the meaning of a smooth measure? That is a smooth function times the big measure. Is that what it
Means locally they're given by smooth functions. On any space, a smooth measure is one that's locally.
function only after multiply.
No. Let's put it this way. Suppose I have any manifold at all.
Okay.
Then what is a smooth measure on that manifold? It's one which is locally given times the big measure in any coordinate system times the smooth function that's independent of the coordinate system I choose. Okay. Okay. It's just infinite. The smoothness is just a local criterion. Okay. Okay. Are there any questions so far? So we have a picture. I didn't draw the picture, but I should have. Yeah, I definitely should have. So the picture I should have drawn, here's a picture of the complex plane. Here's the unitary axis. And this is the imaginary line. Here's 0, but we haven't said anything about 0 yet. Well, that'll come later. Here's 1/2, and here's -1/2. Okay. And this is C infinity quotient G. And this is, okay. And so these are unitary. Now I have a feeling, now, and these spaces are stable under G, so there's no, I haven't said anything about GK yet. These are representations of G itself, smooth in almost any sense you want. Yeah, these are GX on these, by the regular thing. Remember, these are homogeneous bundles, so RG of F at a point X is equal to FG X FG. Okay. Now, the best way to describe this space, I don't know about best way. I said best here, but that's really, we'll see that that's not necessarily, there are really two good ways to do it. This is one of the two good ways. I don't know why I wrote that. I was feeling conventional. So if I restrict my function to K, I get a map from K to C, and it still has to convert on the left in a nice way as long as P belongs to K. So I have this functional equation as long as P is in both. Now, what size is K intersect P? How many elements are there than K intersect P? 2, just 2, plus or minus 1. Those are the only possibilities. So this is very simple. This means I only have a condition on the 2 elements. So the chi determines the parity, and the parity is that number m. Remember, there was a sign in things, and the s doesn't matter. That's trivial on k. But so this just determines the sign. So chi, this is just something to do with the parity of m. Okay, and yeah, that's what I say. So chi minus I is that. So what we get is, by the theory of Fourier series, but for C infinity Fourier series, I don't think that was covered, was it?
You mean the rapid decrease of the?
Yeah.
No.
What should I do about it?
Just say with C infinity, coefficients of C infinity.
Yeah, let me remind you. Let me make the statement anyway, and we might say something about it. That's very important, actually, in this business. So Peter, I think, defined the Fourier series only for L2 functions. But if I have a function on the unit circle, it goes to its Fourier series, Fn times e to the 2 pi I n theta. And the Fn's are equal to O of 1 over n to the k for all k, if n is in C infinity, because f is smooth.
Why don't you say words with big O notation means?
Sure, it means these things, actually, first of all, there's an absolute value around this. These means that these coefficients decrease faster than any possible polynomial, the inverse of any polynomial in n. So for example, exponential decrease is fine, but it doesn't have to be that fast, just very rapidly decreasing. Is that okay? Why is this true? Yeah. Yeah, and the short space of Z, right? Yeah, that's exactly. We'll talk about that next week, probably. As you all know, we're all running a little late here. We were supposed to talk about this earlier in the week, but didn't get around to it. But that's right. It's in the short space of Z. If you want to say that, it doesn't. But the short space of Z is just something very simple. It's just all functions on Z which decrease faster than any inverse polynomial. Why is this? In one word, why?
When you differentiate f, you're multiplying by n.
Yeah, because if I take f prime, then that goes to, I forget, it goes to 2 pi I n times fn. Yeah, and now, so the first, well, you don't even need Riemann Lebesgue. So the first fact is that these functions, as long as f is continuous, then these things are bounded, right? This is just an integral. Fn equals the integral from 0 to 2 pi of f of x, if I think of these as being functions of angle, dx, times e to the minus 2 pi I and x dx. And this is bounded by 1, so this is bounded by the absolute value of f. So if f is bounded, then these are all equally bounded. There's some constant bound for all the coefficients here. And if f is smooth, then this is still continuous, and so these are all bounded. And if I keep on taking derivatives, then all 2 pi I n to the k times fn are bounded. And that's what this says, basically, is it's exactly the same statement. Okay, so those are equivalent statements. So the fact that it's smooth is the fact that works out right. Okay, we'll have to say more about Fourier series a little bit later on, I think. Anyway, that's the basic fact. So that means that if I restrict my smooth principal series to k, it's just a topological sum of characters, and we have this restriction on the parity. So it's the sum of all these characters, epsilon n, where epsilon is the thing which I mentioned before. If I have a rotation matrix, this goes to this. So that's the basic identity character on k. So every function in the C infinity principal series can be written out as an infinite, very rapidly converging series of characters when I restrict to the rotation matrices. Are there any questions? Okay. Okay. And so I can fix, so what, now G is equal to pk, and my function is determined by its restriction to k, and so I can write it out like this. If I have a function, I can define a particular function in the principal series by looking at a particular restriction to k. So I take my character n, my epsilon n rather, I assume that that's what it is when restricted to k, and then I just extend it to all of g on the assumption that chi and n are compatible in parity. And now, how does this work out in practice? Is it a nice explicit formula? It's one of the reasons SL2 is nice. So if I write this out like this, if I take this element, then I can write it as pk, where p is this and k is this. And so I have a very explicit formula. If I assume that my restriction to k is epsilon n, then I can write it everywhere on any element in the group according to this formula. That's because I have this factorization, which I think I gave before somewhere. The g is equal to pk according to this rule. Okay. So this is all very explicit. This is one of the few groups where things are reasonably easy to work out. Okay. So one thing to keep in mind is that I have this whole family of principles. So basically I have two different continuous families. I have one continuous family for m equals 0, and then I have another continuous family for m equals 1. And each one of these is parametrized by the whole plane. These have the property that the characters of k which occur are all the even ones, the identity, epsilon squared, epsilon fourth power, and so on. These have the property that all the parity of the epsilons are odd, epsilon minus 1, epsilon 1, and so on. So these two separate continuous families. And the point is that in some sense, all these representations, as a representation of k, all these representations are the same, but they differ enormously as a representation of g as S varies. And we want to write down explicit formulas for what happens. That won't be much of a surprise because we'll see that we get the formulas that Peter wrote down yesterday. Yeah? Epsilon is the character, it's right here. It's the character which takes the rotation matrix C minus S, these are cosine, minus sine, sine, cosine, to cosine plus I sine S. So if this is theta, this is e to the I theta. Okay, now, I have these basis elements. So the basis elements, phi n is basically epsilon n on the group K. That's a basis element for these things. And what we know is, so I have this group acting on all the C infinity functions, the smooth functions in this space. But I know that what's interesting and gets much less confusing if I look at the K finite vectors. I look at the subspace of these, which are K finite, and the K finite vectors are just finite sums of the epsilon n's. Some animal is eating erasers. So now I have some notation. If I don't write the infinity up there, if I just write this, this is equal to the finite sums of the functions phi n. And this is no longer stable under G, but it is stable under the Lie algebra.
There must be something wrong with this Lie algebra.
What Lie algebra is wrong?
I mean, your base doesn't consist of phrase 0 edges.
Oh, then I've made some horrible mistake. Oh, so it doesn't. Yes. This is SL2 1R maybe or something like that. Okay, yes, these should be minus ones. This is a minus 1 and this is a minus 1. I'd like to blame Don Knuth for this, but I can't quite do that. Okay, yes. Okay, so and this basis we've seen before. Actually, I realize now there's a slightly better bit. Anyway, this is the one that Peter used yesterday with some twist by I or something like that. So this is basically generates the Lie algebra of K, and these are the two things which somehow were the raising and lowering operators on the weights of K. And so we have this identity. This is the commutator. It's Kx plus minus, well, Kx plus or minus x plus or minus K is equal to that. And then yes, so I want to calculate what the effect of these operators on this basis is. And the first thing to note is that precisely because phi n is taken into a multiple of itself, epsilon n in fact, the kappa of this, so this is the derivative of the representation, so to speak. So kappa of phi n is just ni times phi n. That follows just immediately from the fact that k times epsilon n is, times phi n is epsilon n times that. So this is direct from the definition of phi n. And now I want to find out what the x plus and minus do, but I think this is essentially a calculation that Peter made yesterday. I go through this, I use the commutation relations, and we see that x plus or minus phi n is some constant times phi n plus or minus 2. So the x plus or minuses increase or decrease the index n going up or down, so to speak, on one of Peter's diagrams. So that's what we know immediately. We just have to find what the constants are. And, well, Peter showed in a sense how to get those yesterday, but with different data to start with. So we have this equation, x plus or minus phi n is equal to some constant times phi n plus or minus 2. Is there a question? No. And so we want to know the constant. So, yeah, that's right. So the constant is equal to this. I calculate this, and I evaluate that at 1, and that's what the constant is. So I just have to evaluate this thing. And now here's something I've said before, but went over very, very rapidly. We have the Lie algebra. So the group here is acting on the right, and the Lie algebra is acting on the right. For example, we know what our kappa, when I write down kappa phi n is something, that's the kappa is acting on the right. But now we have this funny little equation that r x of f evaluated at g is the same as L g x g minus 1 of f evaluated at g. So, and basically, the way to think of that, if you forget this, which is certainly understandable, the way to think of that is like follows. F of gx is equal to, so this is right action, but now if I can write this like this, and this is left action. So the right-hand part gets translated to the left-hand part after conjugating. And that's what this equation says. And so now I plug that into here. So Rx plus or minus, in this case I'm going to take g equals 1. That's very nice. I get this. And now, so I write out my x plus or minus somewhere. Oh yeah, that's right. I have an expression for x plus or minus in terms of alphas and nus and kappas. And we know what the left-hand side of alpha and nu do. Nu takes my functions to 0. It just kills the functions because my representation is, my character chi is invariant under n. So nu just kills the function, and alpha just multiplies it by s. And then there's the 1, so s plus 1 because I've got that delta 1/2 factor thrown in. So in this case, delta 1/2 of a, so to speak, is equal to a. So it's a squared to the 1/2 equals a. And so L alpha times f is equal to s plus 1 times f. So multiplicatively, I can see somehow we haven't said what we should have here. So multiplicative, if I multiply this times this, it's equal to alpha, s plus 1 times f. And on the Lie algebra level, I just take derivatives, and it comes out to this. Okay. So we can actually write this down, and then we get this equation here, that this constant is equal to s plus 1 plus or minus n, depending on the plus.
What alpha is?
Yeah, alpha. And it's the key thing to remember is its exponential is this. When I exponentiate, then that goes to that. And since the derivative of exponential is this, so that's where this comes from. This is basically, I'm just calculating the derivative of an exponential. Yeah, somehow we miss this. Okay. Peter, do you have any comments?
No.
Okay. Are there any questions? So here's what happens. So so here's the summary of what happens when this thing kappa times epsilon n is this, and x plus or minus times epsilon. Oh, this should be phi here. Yeah, make that correction. I know this should be, there are four phis here. Not epsilons, but phis. Okay. And for example, the representation I did before, that was the constants. The constants s equals minus 1, because that's just the constant functions on the projective line. S plus 1 is 0, and so this just becomes 0, and then it gives exactly the same relations I had before. Otherwise, you get, for some shift of parameters, you get what Peter wrote down yesterday. Okay, and there's no capital H here. Right. And now here's the fact which Dragan mentioned this morning. And in fact, it more or less follows from Peter's calculations plus the calculations I've done here. Every irreducible GK representation can be embedded into a principal series, one of the ones I've already defined. If you match, you can match up the relations Peter wrote down yesterday with the relations that I've written down here. Dragan will prove this sometime tomorrow? No, not tomorrow, Friday. Tomorrow, have we announced it?
We haven't announced the schedule change, but why don't we do that after you finish to announce it?
We want to keep them in suspense?
Yeah.
Okay. Okay. You don't want to make them happy now?
No.
No. Okay. Okay. Postpone your happiness. We'll just leave it as a later lecture. So in a later lecture, Dragan will actually, I don't think prove is quite the word, but make it plausible. Explain some reasons why. A physicist's explanation of why it's true. What's the proof? But yeah, you'll almost prove it. You'll almost prove it. You're not going to prove convergence, though, are you? I mean, proof is proof. That's no. Okay. That's right. That's right. That's right. Actually, to tell you the truth, a little. Actually, I'll give you a benefit. It'll be better than most of the other proofs. I think that's a fair statement. It'll be a pretty good proof. We'll give it 8 out of 10. Yeah.
Why these harmonic functions are equal to in D somehow?
What is your question?
So here on this sheet, space harmonic functions isomorphic to the reduced representation of delta.
Oh yeah. Oh, because it's their boundary value. Yeah, I didn't say that part in my talk. That's right. I forgot about that. So what we have is the following situation. Let's look at what I talked about on Monday. So let me just remind you of a little bit complex analysis. So on Monday I talked about functions on the disk which are harmonic. And I had all these functions. I think I called them the same thing, but anyway, the functions were 1, z to the n, and z bar to the n. And now g acts on this space, but g also acts on the circle, right? These are functions, so the functions on the circle. So I take one of these functions and I restrict it to the circle, and that's a g covariant map. If I transform a function by g, then I restrict it to the circle, it's g applied to the original restriction. So restricting to boundary commutes with action by g. And because I have this very explicit basis, I can see that it's an isomorphism into. On the other hand, every function on the circle can be written, every k-finite one can be written as a finite sum of these. So the space of harmonic functions is isomorphic to the functions on the circle and the explicit isomorphism is given by taking boundary values. This is a special case of a very general fact about asymptotic behavior of matrix coefficients, which again Dragan will explain. Okay. Right. So that's why the two calculations agree. Okay, there's one more topic I want to talk about, but it's somewhat technical. I'm not sure how this is going to sell. Let me say something and we'll see what happens. So the first fact of life is that, so now we have a picture. So let's sort of summarize. We have this picture. We have these two different planes. We have one S-plane, another S-plane. On this one, m equals 0. On this, m equals 1. We sort of understand what the restrictions of these representations to k look like. They're all the same on each one of these two planes. We know what a few individual points here are. We know if I take s equals 0 here, I get the constants. If I take s equals 1, I get the space dual to that. So those two structures are dual to each other at s equals 1/2 and minus 1/2. We don't know anything else really about what goes on. And except that we now know, at least in principle, although we haven't proven it, that every representation somehow occurs embedded in these principal series. Now that's a general fact about arbitrary reductive Lie groups. Every representation, every nice representation of a reductive Lie group occurs somewhere in a representation induced from its minimal parabolic. That's sort of one of the absolutely basic facts of life about representation theory. Now, that doesn't make your task easy because offhand, when you look at these planes, they're just large gray blobs, right? There's no individuality somehow, but in fact, there's a great deal of structure and detail in these blobs. Many different points on each plane are somehow split up in some complicated way. And so, for example, some principal series are isomorphic to other principal series. So the first question to ask is, I have one of these S-planes. What happens over here? So the answer is generically, S and minus S, generically, not everywhere, but generically, S and minus S give the same representation. So that's the first fact of life. That's one thing we want to see. So it's a general case of the fact some principal series. So we want some way of telling whether two principal series are isomorphic to each other. Another fact is that some principal series are reducible. So we want to understand which points over on each one of these planes give rise to reducible representations and what the structure is in those cases. And there are various levels of complexity to figure out what's going on. But either way, the necessary tool for figuring out this is to calculate the homomorphisms from one principal series into another. That's the basic algebraic tool of dealing with principal series. So you want to compute, if I give you a principal series, you want to see what the maps, the G covariant maps are into other principal series. That's the basic tool. And the way to start is by something called Frobenius reciprocity. So let me write something down which is not on the board. So first of all, what we want to figure G of in, say, chi, and I'm just going to write I for short. And I'm going to write G, but it's actually, I guess I should write like this. But maybe G, if I put I infinity here. Okay, something like that. So I want to look at, I'm not going to worry too much about technicalities of G versus just the Lie algebra, but we'll see. When we actually come down to the details, we'll be a little more careful. So this is what we want to do, but it turns out it's just as easy more generally to just look at an arbitrary V or possibly an arbitrary V infinity. So I want to state a general fact, a very simple tool about such things. So I take a Harish-Chandra module, V, and I want to give a very simple tool for determining the maps, the covariant maps from V into induced representation. Now we have the following picture. Okay, so suppose I have such a map. Then I compose it with a map which takes f goes to f of 1. Now, if I take Rp of f and I evaluate it at 1, that's f of p, which is f of p times 1, so that's equal to chi of p times delta 1/2 times p times f of 1. So the map from here to here, this goes into C, so the map from here to here has this property that I'll call this map lambda 1. So lambda 1 times Rp of f equals delta to the 1/2 chi of p times lambda 1 of f. So it's a p covariant map onto this p module with delta 1/2 chi. So if I compose that, it's still true. So if I take, let's call this map capital phi, and now we have the following property, lambda 1 composed with phi of pi of p of f of vector v is equal to delta 1/2 chi of p times lambda 1 composed with phi of v. So that's a very simple fact, and it just follows from the properties of lambda 1. So let me summarize what happens. If I have a G covariant map from V into the induced representation, I compose that with just a simple evaluation of the function at 1, and that gives me a function which is a P covariant map from this onto this module, delta 1/2 times chi. And Frobenius reciprocity says that this is an isomorphism. Now, I don't know. We've talked about Frobenius reciprocity. When I did these notes, I hadn't seen Peter's lecture, so I don't have to say much. Peter talked about Frobenius reciprocity for finite groups. It's just a rehash of that. Yeah, it's just a sort of a summary of what Peter said for finite groups. And this is a summary of what I said. So now we have the following fact. So now what I claim is, and this should have a G here. It's a misprint on page 30. Should be a G here, so, or GK really. It should be Hom GK from V into the, here it's G because I've got the smooth thing there, but just remove these if you don't like the analysis involved. So this is hum GK of this into this is and Frobenius reply says that this map I have over here is an isomorphism between these two sides. So I have a map from here to here, and in fact it's an isomorphism. So, yeah.
This is a technical point. This really isn't equal. These things are actually isomorphic.
Yeah, but it's a canonical isomorphism. Yep. Right. I lecture engineers after all. I tend to write equals when I mean canonically isomorphic.
I have a question about
Yeah.
notation.
Yeah.
Whatever you write RPF.
Yeah, RPF is this is the right regular action. Rx of f evaluated at point G is f of Gx. Okay. It's just the representation on the induced principal series. Isn't no other notation. Okay. And so to determine the maps from any nice representation, any Harish-Chandra module into the principal series, you just have to figure out what these things are. Now, N, I have here the group, and that's legitimate, although that takes a little bit of care, but still that works, because P doesn't really act on V, so I have to, this is not quite right. It should be a Lie algebra of P, it should be there. Now the Lie algebra N acts trivially on this. And so any P map from V to this takes nu plus V to 0. That means it has to annihilate. So if I take a space V, there's a subspace of that I get by just applying nu plus to everything in sight. So if I have a map, if I have a P map from V goes to delta 1/2 chi, then nu plus of any V goes to 0. And so it has to factor through the quotient. Looks like this. So the first step in classifying Lie algebra P maps from here to here is in looking at this space and seeing what this looks like. Now this is actually a P module. This is a module over A, in fact, because N acts trivially. That's the Lie algebra. A is the Lie algebra of A. And so the understanding what these maps look like is a two-step process. First of all, I figure what this quotient looks like, and it turns out to be pretty simple very often. And then I want to decide what that is as a module over A. So that's the process. So in order to understand these intertwining operators between principal series, we have to classify. We have to first discuss what this space looks like, or say something about this space, and then see what its structure is as a module over A. And I'm going to stop here. It begins to get a little more technical, but that's what the rest of this page says. I will say only this, that the Verma modules come up in here somewhere as well. There's some secret reason why they do. So on page 30, I'm really slowing down, but we'll stop there. Okay, that's all for today.